Seasonal UV radiation variations at Lake Tahoe, a new geologic data compilation from DOGAMI and lake coring to find faults. Welcome to the GSOC Geology Hour. I'm your co-host, Alyssa Smith.
I'm your other co-host, Carrie Gordon.
And I'm your special guest, Natalie Culhane.
So, hey everybody, this is my Geology in a Nutshell little segment I do every month here. And we're going to be looking at a few different articles or kind of recent things to come out in geology. So our first little bit here is going to be talking about precipitation extremes and UV radiation at Lake Tahoe. And then the second bit, I'm really excited about this one, is an updated Oregon geologic data compilation from DOGAMI. So first, we're going to talk about some recent work that's been done at Lake Tahoe. And as kind of an overview for this study, this was a part of an 18-year investigation into UV light penetration in Lake Tahoe. So it's a really pretty long-lived study that just got published. And then what they had found is that there's been a dramatic year-to-year shift in the lake that's tied to precipitation cycles in the Sierra Nevada mountains. So the connection between UV light and seasonality. First off, people have been measuring water clarity at Lake Tahoe since 1968. So there's a big amount of data for that. What they've found here is that just because they've been looking at water clarity, that doesn't necessarily correlate to the UV light that's getting into the water at different depths. And the importance of this is that UV radiation can affect chemical and biological processes. So this is a picture from the study itself. So when we're talking about water clarity, it literally means like how deep can you see things in the water? And the way that they measure this is using this white disc, and they let it down in the water and measure essentially how deep until they can't see it anymore. So they use this white disc. It seems very high tech. Essentially how deep is the disc visible is what they look at there. Comparing that to measuring UV radiation, what they do is it's almost the exact same thing, but instead of having a disc on there, they have a UV sensor. So that will tell you how deep does UV light reach in the water. And the important thing this study found is that, the water clarity and UV radiation amounts don't necessarily correlate. There tends to be a really strong seasonality component to it. So why is this important? So we're going to look at the electromagnetic spectrum, or part of it. From the light that we see has a certain wavelength. So depending on what color it is that you're perceiving, the light is between 400 and 760 nanometers between, if you go peak to peak or crest to crest, a similar point on a wave to the next one, right? Light that is slightly longer wave than that we wouldn't be able to see with just our eyes is called infrared radiation. And then if you go beyond that, that's when you get into like radio waves, radar, things like that. The longer wavelengths here are going to have lower energy. So that's really important, especially when we go in the opposite direction. If we go into the point where we've got shorter wavelengths, those tend to be, that's where our ultraviolet radiation is. So it's between 10 and 400 nanometers. And these shorter wavelengths tend to have higher energy. This is what's really important when we start to think about the effects to biological and chemical processes. So these UV fluctuations, what they determined is that there's huge fluctuations that are tied to precipitation cycles in the Sierra Nevada mountains. So years where there's a drought, they see that there's a significantly deeper UV penetration, and that's sometimes up to 4 times as high in summer. And the energy of those wavelengths, they said, is up to 100 times stronger, 10 meters or 32 feet below the surface. So that's compared to wetter years. And in wetter years, the sort of UV light is not getting in as deep. So why? Largely what happens is that in wetter years, you have more like seasonal runoff. And so you're getting more water input into the lake. And with that water is carrying particulate that could be really fine particulate. And that particulate is what is going to block UV radiation. So that's why this is important. So what are the implications for this? The UV radiation balance in these systems is incredibly important, and high UV radiation can cause damage to DNA. It can inhibit photosynthesis, and it can affect zooplankton, which is what the picture is here on the slide. There is, I guess, kind of a silver lining. They do notice that the higher UV radiation can inhibit the reproductive cycles of some invasive species like bluegills, essentially making it so the only places that they can spawn is in really murky waters. So probably not worth the other effect, but it is notable. It's something that happens. And so the overall impact with this is that these large shifts in UV radiation can cause changes to ecosystems, and then meaning that precipitation cycles can lead to biological damage. So essentially what the study said that they could see happening next is utilizing the fact that there is a large amount of data for Lake Tahoe. So whether we're thinking about the water clarity data that's been measured for, what is that, 60 years? I can't do math that quick, apparently, since 1968. Yeah, so the better part of 60 years. And then they can use this UV data from the past 18 plus years now for continued monitoring. And with continued monitoring, that they think this is going to be really important as climate change progresses. And the next thing that they suggested studying is looking at how UV variations can impact the carbon cycle, as well as some other biological processes. So yeah, neat study. Highly recommend checking this one out.
Did that study indicate that they would be looking or trying to compare any of the northern lakes that have got some of that same long-term data associated with them?
They did say that they recommend that it be done in those places. So that was like when they're asking the researcher at the end, like, what do you think people should do next? They're like, well, we should be looking at other lakes worldwide that have big amounts of data, because this is not just something that's going to affect Lake Tahoe. This is everywhere. So yeah, wherever there are data that are collected and like readily available, seeing if they can kind of compare that. I know it's the clarity data and the UV data are not the same, but my thought is like if they can see correlations, if they can find some sort of quantification to tie the UV radiation and the clarity together, maybe they can use that to see estimates of UV, even if they don't have those data available, is my thought. So the next bit, there we go, is a recent update to the Oregon Geological Data Compilation that's been put out by the DOGAMI. So first off, what is this thing? It's essentially a paper. This is kind of what it looks like. You can look at it online and download it for free, which is really neat. Well, that's cool, Alyssa, but what's in this? So what this has got is there's informational pamphlets that kind of tells you what data went into it, what all the different stuff is that's included. And then there's 6 map plates and also an entire GIS data package that you can download. So this map shows the different regions that are included. They broke Oregon up into 5 different areas. So we've got the Northwest, we've got the Southwest, Southeast, Northeast, and Cascades. So different map for each of these. So let's take a look at what these things look like. Oh, also time rock charts. That's the other part to mention. So that's what I'm going to show on the next one. So I'm just going to skip that. Here we go. So time rock charts. What are these? It's essentially a way to have graphical representation of ages of different rock units, then the stratigraphic relationships between different rock units. And that's really important for illustrating the absolute age spans and looking at temporal relations, like how are different units in different places going to be visually, like how can you visually compare them? So let's take a look at one of these maps. So if you open one of the map pages, that, what do they call them, plates, this is what it's going to look like. So this is the Northwest Oregon one. I didn't choose the Cascades one just to show I'm very biased towards my field area. So this is the Northwest portion. We're going to zoom in a little bit here. So there's an introduction here on each of the maps. It'll just tell you this is what is included on the map. There's the location map that shows you where in Oregon these map units are included. And then there's a little tiny little geology map that the colors should be lining up with the ones that are on the chart below. Now, we look down here, this is where we've got kind of the stratigraphic relationships. So at the top, it'll show you the different areas that are included on this map. It's got the time along the y-axis there. And on the left-hand side, you've got the geologic times. So you can look either if you want to say, okay, what was happening in the Quaternary? You can do that, or you can look at actual numbers. And then here are the compilation units. So this in itself isn't going to tell you a lot. That's why you've got to go to the side of it. Here we go. So there's a lot of different stratigraphic units here. For each of these, they are arranged alphabetically within the different packages. So the unit label, that's what's going to be on the chart to the left. The compilation unit name, so what did they group into that? And then the terrain or the group. So that's what those whole packages are there. You can look, if you're looking just for the Columbia River basalt groups, you can look in the one color, then you can look at each of the different units within that. And then the percent of the area that covers. So really neat way to visualize the data. And as you can see, there are quite a few included on each map. So it's really neat. You could kind of stare at these for a long time. I know I did, and that's really neat. So if you have GIS, you can put these into ArcGIS and you can use those. I've done that before with one of the previous data compilations, so now I'm going to go in and update it. But there is also a way that if you don't have GIS and you don't want to have to deal with that, there is a map viewer online. The one thing with this is that this is not updated to the version 8, the most recent release. But if you're going between the different ones and you're trying to say, okay, well, I want to look in this general area, where did they get this information from? You can go and you can use the interactive geological map web app. So that's really neat. So again, it's just for release 6. They haven't updated it to 7 and definitely not up to 8. I don't know why. I don't know if that will change, but it's really useful as is. So what that would look like if I was using my computer to show you, I guess I technically am because it's a presentation. But if you were to go in and look, this is what you're going to open it up to. It's going to have the state of Oregon and all the different terrains and units and whatnot. And then what I recommend doing is coming in and you could change the base map. I prefer this one, the terrain with labels. You can also put it on LiDAR. You can put it on topography. There's a few different options. This one I think is just the most clear. And then you can zoom in. That box wasn't supposed to show up yet. But if we're looking at Portland here, you can see that there's all kinds of different boxes on there, which is what I was trying to show. And that shows these maps were made from, I don't know, dozens and dozens of other smaller maps. So a lot of those maps tend to be different scales and different kind of resolutions. So you'll see, if we go back, you can see that there are boxes on there. That's just why. So if you're like, why, what is this weird thing that's happening geologically? It's not geology, it's map resolution. And another thing that's really neat that you can do, and I think is my main reason for pointing this out in case anybody's curious, is that if you want to click on a specific map unit and you want to figure out what map that was sourced from, you can click on an area. So I just circled Cultus Mountain here, and you can zoom down and it will tell you what map that one came from. So if you go to more info, usually it'll link you to the map page. If not, you can just highlight it and put it in Google and that'll take you there. It's really helpful though for trying to figure out where was this information taken from. Really cool new thing. I highly recommend everybody check these out. They're free. You have a right to see all these data and everything. You can mess around with it. And yeah, just know that's there. Last thing I want to say, if anybody is looking to do some hikes in Central Oregon and wants to be a part of research and is okay like swinging a hammer and taking some rock samples, talk to me. Send me an email because there are areas in Central Oregon that I'm not going to have time to get to. But if any of you are out there anyway, just let me know. And yeah, you can put your name on my research.
Natalie, I think we're about ready for you. And we're going to learn about understanding Mount Hood's Twin Lake faults. Oh my gosh.
Yeah, let's dive straight in. So just briefly, this is my master's thesis. So this is what I've been doing for the past 2 years or so. I'm Natalie Culhane. I'm a second year, almost graduated master's student at Portland State University. And my thesis has been focused on the lacustrine and terrestrial paleoseismic records of the Twin Lakes Fault near Mount Hood in Oregon. So just to give a brief overview, the Twin Lakes Fault is an extensional crustal fault that parallels the Cascade Volcanic Arc. My work over the past year has revealed evidence for multiple surface rupturing earthquakes on this fault in the late Quaternary, which means since the last 1.5 or so million years. These findings contribute to a broader tectonic picture of regional extension, as well as characterize the Twin Lakes Fault as a local seismic hazard. And here on the right, you can see this is a 3D map of Mount Hood looking northwards towards the summit. The Twin Lakes Fault is shown here in red, and the bright blue shapes are small basins found west of the fault trace. And my study has focused on 2 of these basins, and I'll speak more about them in a moment. So to set the tectonic stage, some of you might already be familiar with this, but for at least the last 16 million years, the North American plate directly east of the Cascadia subduction zone in Western Oregon has been rotating clockwise and translating northwards. This animation by Wilson and McCrory is showing that movement of that block. So it's showing that rotation. I'm going to play it just one more time so we can see that. So this westward and northward movement creates a space problem within this continental plate. Extension in the crust east of this block is accommodated through 2 different processes: magmatism, forming new crust, and faulting in North America's interior. Here, this figure, you can see the USGS mapped faults in dark red, and I've highlighted in bright red those that provide at least some extension across Oregon's Cascade Volcanic Arc. So I'm going to now focus in on the Cascade volcano Mount Hood. The Mount Hood fault zone consists of about 40 kilometers of primarily extensional faults that trend north and south from the volcano, which are shown here colored by individual fault strands. Historically, this fault zone has experienced low magnitude earthquakes in swarms spanning days to weeks that exhibit primarily extensional slip. And this figure shows the hypocenters of all recorded earthquakes that have occurred around Mount Hood since we've started recording earthquakes in 1970. And I've colored 6 different swarms that have occurred in the past 20 years. They're a little hard to see because they're all overlapping, but you can see overall across all of these earthquakes, some regularly occur directly beneath the summit, and that's presumably along the volcano's main magma chamber. However, these swarms that I've highlighted, as well as most other seismicity clusters between the Mount Hood summit and my study's focus, the Twin Lakes Fault. The Mount Hood fault zone has also experienced major surface rupturing earthquakes. So 3 different paleoseismic trenches have been excavated over the past 10 years across the fault zone and have found evidence for at least 1 fault rupture since the last glacial maximum, which I'm going to be abbreviating as LGM, which occurred around 19 to 21,000 years ago. Focusing in south of the summit down here, I'm going to zoom in now. The Twin Lakes Fault trends north and south for about 16 kilometers. It's a west dipping normal fault consisting of multiple uphill facing scarps. And I'm going to show this diagram here is what an uphill facing normal scarp looks like. So the upslope side gets sent down. That's called the hanging wall. The downslope side gets sent up. That's called the footwall. And this movement allows for impoundment against the fault trace. And you can see that here with this red. And so what you see for much of the Twin Lakes Fault is that impoundment, that collection collects both sediment as well as water. So a 2021 trench excavated on the northernmost edge of this fault found evidence for 2 surface rupturing earthquakes. The most recent event was bracketed to occur after Mount Hood's timberline eruption, which has been dated to about 1,500 years ago. I'm going to focus in on 2 depositional basins that are bound to the west by this fault, which are Lower Twin Lake up here and Frog Lake down here. So zooming in on both of these, both basins have outlet channels that should drain eastward based on the topography. So you can see that to the east. However, as you can see in these topographic profiles up here, these channels are instead vertically offset from modern lake levels. So they're uplifted from modern lake levels. And before my investigation, we guessed that these basins were fault bound with movement of the fault's hanging wall down dropping the lakes, shown here as D, and upthrowing the eastern shorelines, shown here as U, which abandon those drainage channels and allow for sediment and water ponding, creating these two lakes. Now, the presence of these lakes is a unique opportunity because lakes tend to capture a more continuous and higher resolution sediment record than deposition on land. And you'll see that on my findings in a moment. So just to sum up this setting, we have short-term seismicity as well as paleoseismic trenches that suggest extension in the region. We also know that over millions of years, the long-term tectonic setting suggests that this region has been experiencing extension for several million years. And my study bridged this gap to investigate the unknown, an intermediate history of fault ruptures, surface rupturing earthquakes on the Twin Lakes Fault. And I approached this question using several methods. On dry land, I investigated structural and stratigraphic relationships in a small hand-dug paleoseismic trench. I also improved superficial geologic mapping along the fault trace. And at Frog and Lower Twin Lake, I invested subaqueous basin morphology and lake stratigraphy by performing both geophysical surveys and extracting, interpreting, and dating several lake sediment cores. So let's start with the terrestrial evidence. Our trench targeted an uphill facing scarp, so I've shown that diagram once again, between Frog and Lower Twin Lake. And this is a topographic profile of our trench site showing that what that actually looks like, one of those uphill facing scarps in the LiDAR. Our trench site had about 4.5 meters of vertical bedrock offset, and that suggests a history of multiple surface rupturing earthquakes. I and a team of field assistants hand excavated a small trench here last September, which involves fighting with several large boulders, including the one about the size of Sandy, my fellow grad student, on the bottom left. We ended up with a trench that was about 5.5 meters long and 2.5 meters deep, and you can see that on the picture in the far right. Now, here's a photo of one side of the trench, and below I'm going to show the interpreted sediment units within that trench wall. I'm now going to be showing you evidence for 2 surface rupturing earthquakes that we've interpreted from this trench. First, we find evidence for earthquake 1, or E1, and I've highlighted that here in purple. At 2 separate fissures, we found very loose silt to cobbles and the cobbles were so loose we could pluck them out of the wall by our hand. This infilling material contained stacked cobbles that follow the general borders of the fissures. So these are 2 fissures, one here toward the northeast and one here more towards the center. And in the northeast fissure, we actually found chunks of a lower unit. So it's a little hard to see, but these yellow colored cobbles were actually pieces of this underlying unit called glacial till. And glacial till is material that gets deposited and dropped by glaciers as they're melting out. And so because of this, we've interpreted this as, as the fissure happened, it basically tears apart the wall and grabs pieces of the wall as it goes. So next up, we have evidence for E2, or earthquake 2, that I've highlighted in green here. The larger green here, or called unit 30, is a unit we interpret to be a colluvial wedge. And I've shown a diagram on the far right as to what a colluvial wedge is. And it's the material that falls off that upthrown block and gets deposited on the downthrown block of a fault after a rupture. This wedge overlies a fissure labeled here as unit 35 here in lime green. And that's another unit that is infilling a fissure, very loose, very unconsolidated material. Now, evidence for both these earthquakes cross-cuts, let me zoom back again, cross-cuts this glacial till. So these two yellow units below. And so because we have this glacial till being ruptured and being offset by these two events, we can interpret this to mean that there have been two post-LGM surface rupturing earthquakes on the Twin Lakes Fault. Okay, so I also said at least because it's possible that an additional rupture has occurred that wasn't captured in this trench. Terrestrial settings tend to be a little bit more discontinuous. Also, at this site, deposition tends to occur very slowly. So there could be more than those two earthquakes that we captured. Now, to validate these findings from the trench and find evidence for a longer term history of repeated surface ruptures, we need to explore sites of possibly greater bedrock displacement, where deposition has been continuous for a longer period of time. And now we're going to focus on those two depositional basins, Frog Lake and Lower Twin Lake. And we're going to start with improving the geologic mapping around the lake. So just to show you guys again, these are those two lakes once again. We improved the local geologic mapping around the lake using fieldwork and LiDAR analysis. This was the original map that we were working with that was published in 1995. And here's our improved map shown here on the right. We find local bedrock of andesite and dacite. And these are two representative photos here. And this bedrock occurs southeast of the two lakes. Now, past mapping by the 1995 map, Sheridan Scott, dates these two bedrocks to around 1.4 million years ago. So very young as far as bedrock goes. You can see that much of the area around the lakes is shown in yellow. Now, this yellow means glacial till. And so that's that melt out the material that I previously mentioned. And finally, on the eastern shore of both lakes, shown here in the maps in pink, are light-colored fine-grained silts we interpret to be lake deposits. They're only observed on the surface on the upthrown block of the fault. And on both of these maps, the fault is shown here as this red line with the ball and tick symbol. And so because they're on the upthrown side, this suggests that they're uplifted from the lake floor during a fault rupture. And dating charcoal from one of these deposits at Frog Lake, we find an age of about 8,000 years ago. And if this interpretation is correct, one or more of these surface rupturing earthquakes must have occurred after this time. Together, these offsets in the bedrock, as well as the uplifted lake deposits, suggest repeated surface ruptures in the Quaternary. So I'm going to now focus on the modern submerged lake deposits, as these can capture a longer term, more continuous stratigraphic record. We started with geophysical surveys. And just to give you a brief overview, there's two different types of geophysical surveys that we used. Both are active sonar, which means we used equipment to send sound pulses into the water and recorded what bounced back. There's two different types. Multi-beam sends many pulses at once that form this sort of ray into the water. They bounce back once they hit a surface. And this survey records a 2D map of lake topography, which is called bathymetry. Single beam surveys with a different frequency, shown here on the right, use one pulse at a time, and these can see into the subsurface. And they produce cross sections because they're just a single ray. You see basically like this single cross section view of the subsurface called seismic profiles. And so this can give us kind of like insight to what's occurring below the surface in the sediment. And so both of these pictures are showing these, massive research vessels. These two lakes are, high up in Mount Hood Wilderness, and one of them is only accessible by 2 miles along the Pacific Crest Trail. So we obviously couldn't use these, and instead we made do with a lightweight, non-motorized approach, which was 2 stand-up paddle boards that we secured together using ratchet straps. The geophysical company Norbit was a really good help, both in the field and in post-processing results. So this is their representative here, Cody, who's great in the field. So I'm going to kind of show you what those found. Okay, so first off, we have that multi-beam survey, which produced bathymetry of the lakes. Here in these maps, shallow regions are shown yellow, deep regions are shown in dark purple. We find that in both lakes, the deepest regions are also found next to the steepest slopes, and these occur right up against that eastern shoreline at the interpreted mapped fault trace. Now, I've merged this new lake bathymetry with existing LiDAR of the site, and we can see basin morphology across both the land as well as the submerged surface. So I'm going to show two different profiles here, F to F prime and E to E prime. So these are topographic profiles across both basins. The blue line here shows modern lake levels, and the orange lines are showing the locations of captured sediment cores. So these right here, and I'm going to speak to those in a moment. But you can really notice the dramatic difference in slope between eastern and western shorelines. The western shorelines are very gradually sloping, and you almost don't see a difference at the actual modern lake levels, whereas the eastern topography is very steeply sloping. And we are interpreting this as a function of fault movement up throwing that eastern block, with offsets of multiple meters between the eastern lake shore and the lowest lake depths. These merge profiles strongly suggest a history of multiple surface rupturing earthquakes over the Quaternary. Next up, we have those single beam surveys that are taken along single profile lines. These reveal profiles of the lake's subsurface, and I'm going to focus on just one of them in the interest of time, from A to A prime at Lower Twin Lake. This profile, it's a little confusing to interpret, and it takes me a while to interpret as well, but in general, it's showing denser material as darker and less dense material as lighter. And each light or dark layer is called a reflector. We estimate through converting travel time to depth that this profile reaches a depth of about 12 meters. And I'm going to walk through a few key findings from this profile. First up, this location in red shows several reflectors that appear totally cut off or truncated. We interpret this to be a secondary fault that is submerged and concealed beneath modern lake sediment that further down drops that lake center, forming a graben structure. Next up, outlined here in green, are several reflectors that onlap or drape over existing lake sediment. And I'll do kind of like a back and forth so you can kind of see how they pinch out. But yeah, so these reflectors do pinch out with increasing distance from the main fault trace. And we interpret this to be something called gross strata. And this is deposits that take advantage of an infill space left behind after a fault moves and allows for that space. So, you know, as this occurs, it leaves this space and sediment wants to accommodate that. And finally, you can see more of this accommodation in the background lake sediment. And so you can see up here, the background deposits are thinner, and as it goes down, these background deposits are thickening. So not only do we have this individual growth strata, but we also have the thickening of the background sediment. And in that increasing growth, we see about 2.2 meters of measured accommodation space. So what do these layers actually look like? To find out, I and a dedicated field crew spent 2 weeks last summer extruding sediment cores out of both Frog and Lower Twin Lake. Like I said, Lower Twin is 2 miles up the PCT. And so this involved hiking a full piston coring setup 2 miles in. And a full piston coring setup involves everything that you see here on the right. It's both these two massive inflatable like whitewater rafting rafts, as well as a plywood platform, as well as a ton of metal rods. And so this involved enlisting the help of over 20 volunteers to help get that stuff both in and out of the site. And these are some of them on the bottom left. And I really couldn't have done this research without the help of a lot of volunteers. So, okay, so now let's see these two lakes once again, but now I've put in those coring locations shown here in red circles across both lakes. we generally tried to follow the seismic profiles. And so we're trying to get a transect that runs perpendicular to the fault. So we brought all of these extracted cores to Oregon State's NSF coring facility, where we split. So we cut all cores in half and scanned each core through multiple instruments, including the OSU Veterinary Clinic's CT scanner. So here's 3 representative cores from Lower Twin Lake with all the collected data. I don't have time to kind of run through everything here, but for the rest of the presentation, I'm going to focus on 3 things: the high resolution imagery, which is shown here on the far left. Next to that, we have the CT scans, which are shown here in black and white, where white is denser and black is less dense. And I'm also going to focus on the far right. The green plot is CT data. So this was taken at much higher resolution than the green and blue plots. So between all these cores, I identified sediment units that I interpreted as deposits from what I have called rapid sedimentation events. So these are, deposits that are coarse grained, and they're shown as lighter in the CT scans because they're more dense. They're also shown as dips in the CT data. And so I've correlated all these different deposits across all the cores. And I'm going to show you kind of what that looks like across one of the transects. So this is kind of a lot to take in, but this shows just across the southern transect, all the cores collected and different RSE deposits. So these are deposits that are created by a rapid sedimentation event, some sort of pulse that sends coarse sediment into the lake. Throughout Lower Twin Lake, we identified 8 unique RSE deposits, and you can focus on the fact in this figure that many of these units change thickness across the lake. Some units do not cover the whole lake floor, some only occur at the lowest points of the lake, some occur even as the lake starts upsloping towards the shoreline. And these change between thicknesses as well as other criteria kind of gave us clues as to what could have caused these deposits. Okay, so how can we figure out a history of earthquakes from this list of RSE deposits? And I've used past lake studies to apply some criteria, such as changes across the lake floor, which I've talked about, to interpret the events that created each of these RSE deposits. And I identify 3 possible source events for RSEs at Lower Twin Lake. First up, flood deposits will span the entire basin. Deposits from volcanic eruptions will have abundant glass shards and can either blanket the entire lake bed or be reworked into the lake's depot center. Or earthquakes will pond material at the depot center in massive deposits with a clay cap. Now, this is a result of shaking causing first underwater slope failures and then a sloshing of waves back and forth across the lake called a seiche. And you've probably witnessed something similar in a bathtub or pool. So it kind of sloshes back and forth and it sends all of that material ponded at the lake's depot center. So using these list of characteristics, I added up the likelihood of each source event to each deposit and identified 3 units in Lower Twin Lake that can be attributed to an earthquake. Now, there's a lot of background ranking, adding up likelihood of different events, but these are kind of the end results, and I'm going to walk through briefly each of these RSE deposits. So focusing first on unit K. So I interpret this unit to result from one of those earthquake-induced seiches, that sloshing and reworking of sediment. This unit has a sharp to erosive base. It's thickest at the lake's depot center. It is not present on the steep slopes, and it has a clay cap shown as very bright in the CT scans. Next up, we have Unit L. Unit L only appears in some of the lowest collected cores. It has massive sand that punctures the background lake sediment. And this matches characteristics for something called a sand sill, which is caused by liquefaction. Now, these occur when an underlying water-saturated sand layer behaves like a liquid under strong shaking and is forced upwards, and it punctures through existing clay. So since the sand pushed through overlying sediment, the timing of the earthquake that caused it must be the same as a higher up, shallower deposit. And unit K, which I previously mentioned, directly is immediately above unit L. And so I interpret that both these deposits were caused by the same earthquake. And finally, unit G is our thickest RSE unit. It has a lot of glass, and analysis by the USGS TEFRA lab has correlated these glass shards to the Mount Mazama eruption, which is where Crater Lake currently is, which occurred 7,600 years ago. There's a couple diagnostics in this unit that indicate an earthquake deposit, despite this very clear sign that this is Mazama ash. In some cores, the unit presents as massive coarse grains with a clay cap. We also see soft sediment deformation. And so this is, any sort of deformation in looser sediment. So you see this little offset here. You can also see some deformation within LT7 here. And finally, at the core that's closest to the fault trace, we see rip-up class. So we see pieces of underlying lake sediment. We also see pine cones and abundant organics. And because of this, I have been interpreting unit G as both, the source of the material is Mazama eruption. And I interpret that it was also reworked during an earthquake event soon after the initial Mazama ashfall. So summing up all this evidence, I've identified 2 post-LGM earthquakes in this shallow sediment. This is now an age model that I produced from organic samples from a few of those lake sediment cores. This is going through some modeling and trying to actually determine the ages of those units. We assume that the base is the last glacial maximum, which I mentioned was 19 to 21,000 years ago. With this boundary, we find that the earthquake that deposited units K and L occurred between 15 and 20,000 years before present. So it's pretty wide range, but we're still working on honing that down to a finer scale. Considering unit G is composed of Mazama taphra, its age range closely matches that of the current age constraints for the Mazama eruption. Obviously, the earthquake event that would have occurred after would have been post that eruption. And finally, we can also incorporate the earthquake that has been dated in the 2021 trench, which I mentioned at the start, that occurred post the timberline eruption. And the timberline eruption, glass associated with the timberline eruption has been tied to units that were at the very upper limits of these cores captured. And so, above these captured sediment cores, we have a third earthquake. So together, this suggests that 3 earthquakes have occurred on the Twin Lakes Fault over the deposition of the upper 1.7 meters of sediment in Lower Twin Lake. It's possible that older sediment in these lakes capture additional post-LGM earthquakes, but we couldn't get any deeper than what we got. So this is what we have to work with. Okay, so I'm gonna sum this up now. The paleoseismic trench stratigraphy produced evidence of at least 2 post-LGM earthquakes. The abandoned lake deposits east of both basins suggest that multiple earthquakes have upthrown that eastern shoreline since LGM blanketed and reset the landscape. The gross strata in seismic profiles adds over 2 meters to the thickness of post-LGM deposits, and the 6 to 12 meters of vertical offset between lake floor and that eastern shoreline suggests that the fault has been active pre-LGM. Finally, the upper stratigraphy captured in the lake sediment cores provides evidence for at least 2 and possibly 3 earthquakes post-LGM. So summing this up briefly, and I think I'm running out of time, but we find stratigraphic evidence and age constraints for 3 earthquakes after LGM, with morphology and geology suggesting additional earthquakes that have happened in the Quaternary before LGM. Now, taking these 3 post-LGM earthquakes, we can find a recurrence interval, which means, how frequently earthquakes have occurred. And this recurrence interval is between 6.3 thousand or 6,300 and 7,000 years between surface rupturing earthquakes. Now, scaling relationships that we know about between, rupture length as well as offsets estimate that the full rupture of this fault would produce a 6.4 magnitude earthquake. Global earthquakes of this magnitude have caused significant threats to life safety and infrastructure damage, while our current age estimates for surface ruptures don't predict a similar event to occur on the Twin Lakes Fault anytime soon. My findings suggest that the Twin Lakes Fault is a late Quaternary and Holocene active structure that should be considered in regional risk analysis. And here's a list of all the countless volunteers and assistants that I've had throughout this project. And I thank you all for listening to my presentation, and I welcome any questions.
Oh, Natalie, it made me tired watching you guys hauling all of that steel up to drill the, oh yeah, that coring is hard work, and you guys were really creative with what you managed in the way of gathering data. That's fascinating. Totally
Thank,
fascinating.
thank you. It was quite the summer I had last year.
There was a question about how likely is Mount Hood to erupt in the near-ish future, or is that the faults that you were working on, are they not related to the volcano per se?
Yeah, that's an excellent question, and something that I, as well as my lab, as well as local scientists, have been kind of debating is this relationship between crustal faults around these volcanoes and their rupture histories. And if you look at the timeline for, when these ruptures have occurred, um, there's some relationship between like eruptive patterns of Mount Hood. Um, I don't think we have any predictions available for future eruptions of Mount Hood. Um, it is possible that, as an eruption is happening, there's changes to the heat, and there's also changes to how thick how thick the crust needs to be, or how thick the crust is that can hold stress. And so, faults is a release of stress. And so if there's a thinner amount of crust that's doing that, then it might want to pop off. And so it's very possible that if there is like a large eruption that happens, that some of these crustal faults will rupture. But it's not like a, slam dunk correlation that we're finding in the data.
Okay. The next question that came up is, and we can see the photograph here. Where did you find 20 willing volunteers? That's pretty good friends you got there. You realize that, don't you?
Through asking everyone I possibly know. Just like looking at this photo alone, I mean, there's paid undergraduate assistants. There's people I found through Brett's Club, which I don't know if any of you are part of Brett's Club. There's friends and fellow grad students, and uh, my advisors, including Scott, who I believe is still on this call. So it was definitely this massive group effort, and I'm so grateful for all the help, because I we would have made it work with less, but it would have been a lot more tiring. So
Thanks everybody for coming and joining us this evening. Folks, come and join us in September because Andrew is just amazing.